So the last major topic to cover involves what we call radical chemistry, and this is going to be different from the chemistry that we've done so far, mainly because we're going to be dealing with single electrons. So up until this point, basically everything we've done has involved lone pairs of electrons, and so everything is a series of 2 electron processes. But now we're really going to be dealing with a single electron at a time, so that's the major change. So 1 electron at a time is represented by a dot, and then arrows involving 1 electron at a time have a single head on them. So a single-headed arrow is the movement of a single electron, as opposed to the arrows you're more familiar with. So what this means is that now you're going to see things happening like this, where an oxygen-oxygen bond I've already described as being exceptionally weak. And so rather than breaking in 2 electrons at a time, as I've shown you with peroxides, a peroxide can also break 1 electron at a time and just simply fragment down the middle, what we call homolytic cleavage, just breaking right in the middle in both directions. And likewise, bromine-bromine is an exceptionally weak bond, and so you can have bromine-bromine simply fragment like that. Sometimes you will find that the formation of a radical leads to a cation or an anion, but if you count up the total number of electrons that this oxygen has, we split this bond 1 each direction, of course, so this oxygen has 6 electrons on it. It is a radical. It has only a unpaired electron here, but it has 6 electrons that belong to it, so this oxygen is formally neutral. Now it will react as though it desperately wants another electron, because of course it does not have a full octet, but it will do so 1 electron at a time. Likewise, if you have a bromine-bromine bond and it fragments, what you end up with now are a pair of bromine radicals. So 3 lone pairs that were present before, and now the new single electron. One of the key features of radical chemistry is that it doesn't work the way the other reactions that we've followed have gone. And what I mean by that is almost always in radical chemistry, what you have is a chain mechanism. Basically, a very, very small number of molecules is active at any one time, but they just propagate throughout the entire mechanism. And so what you'll have in any radical mechanism is some initiation step. What happens is about 1% of a really weak bond breaks and causes radicals to form in the first place. If you have bromine serving as a reagent in a radical mechanism, then about 1% of that bromine will just go ahead and break, and that causes the radicals, which then carry out the rest of the chemistry. Once a radical has formed, it then propagates through the material. A radical will bounce into something that doesn't have a radical, steal an electron, which creates a new radical. That new radical then goes and bumps into something else, which creates a new radical, and so on. So what's happening is the radicals are constantly being chewed up and regenerated throughout the chain part of the mechanism. One thing hits another, which leads to another, and so on. The main point is that you only have a very small amount of radicals at any one time, so the odds of 2 radicals encountering each other is fairly low. But the mechanism will come to an end when the 2 radicals eventually collide, which terminates the mechanism. If you have a bromine that can dissociate, this will initiate a reaction. These 2 bromine atoms that are currently in a diatomic form of bromine can fragment to become 2 radicals. And so here are the bromine radicals that form. And that will happen because it's a really weak bond. And so if you shine some light on this, or you heat it up enough, or otherwise disturb the system, it can just simply fragment and create 2 radicals. Now these radicals are both formally neutral. Again, there's 7 electrons around this bromine, 7 electrons around that bromine, so they're not charged. And so these radicals aren't attracted to each other in any way. They are not currently content because they violate the octet rule. On the other hand, neither one of them is positive or negative, so there's no particular attraction between these 2. And so more than likely what happens is once you form these radicals, they spin off in different directions and go do other chemistry. They encounter other molecules, rip electrons off of those molecules, and continue to react. But eventually what can happen is that these 2 radicals can encounter each other, and if that happens, the result of bringing those 2 radicals together is that you reform the bromine-bromine bond that you had in the first place. And this is going to be an equilibrium process. You can fragment this, but clearly if the 2 radicals encounter each other, they will recombine. So this is back and forth. So what we have is initiation. A small amount of these fragment to form these radicals, which then participate in the rest of the reaction, but eventually the mechanism is terminated because 2 radicals collide, which then uses up the radicals and reforms a neutral stable species. Initiations are very frequently done via some other reagent that you add specifically to cause the reaction to initiate. For example, we can throw in a couple % of a peroxide, heat it up, or add some light to it, or some other sort of radical initiator, and what that does is generate a pair of oxygen radicals, and then those radicals can go ahead and cause other radicals to form. The species that's formed initially, the radical that's formed initially, does not necessarily necessarily need to be the radical that carries out the bulk of the chemistry. You just need to get some radicals to form in the first place via some initiation. The bulk of the chemistry is carried out by radicals, and eventually the mechanism ends because two radicals encounter each other.